Okay, so this is going to be the bonus session when we discuss about how do we take a derivative of Flory-Huggins series to obtain what we have talked about in terms of combining the osmotic pressure in a thermodynamic way, and as well as from the second law of thermodynamics. Okay, so let's talk about osmotic pressure. Okay, so and what are we gonna do today is and link it together with the Flory-Huggins theory. Okay, let's keep. What is the relationship between these two, and how do we understand them? And this is the part where we're gonna come into play, and let me discuss the mixing in terms of in the Flory-Huggins theory. Gonna be N1 log phi 1 plus N2 log phi 2. Okay, plus N1 phi 2 chi, and that's what is we get from the system of them in terms of mixing energy, right? You could also, in the previous lecture, we also talked about the chemical potential in. Let me write it correctly. This should be defined. The chemical potential in the mixing is going to be equals to osmotic pressure multiplied by V1 is unit volume. It's going to be related to this particular relationship, and you would have delta Gm divided by N1 at constant pressure, temperature, and N2. And in the class we just talked about, it comes down to we just need to consider what is partial derivative in terms of delta G and M1, then we can link this osmotic pressure term to delta G, or using this very simple elegant equation. So what we need to do is now understand delta Gm, take a partial derivative of M1. It sounds like a very long derivative equation, but it's not that bad at all. So let's go through this derivative is what we're gonna do. N1 log phi 1 plus N2 log phi 2 plus N1 phi 2 and chi, and we need to take this as partial derivative as N1. So how do we understand this? And I think it's very straightforward. We need to understand several unique terms, and we know that N1 partial derivative N1 is 1, and N2 partial derivative N1 will be equals to 1 minus N1 partial derivative N1. This will be the minus 1. So these are the two simple ones, right? We know what is those two relationships are, but now we need to consider what is phi 1, take a partial derivative. So we're gonna use next slides and discuss what these two are. And phi 2 is going to be just negative phi 1. What we have talked about is we just need to understand what would be delta phi 1, take a partial derivative of N1. And this is quite straightforward because we know that phi 1 will be equals to N1 plus N degree of polymerization plus N2, and take partial derivative of N1. And we also know that how does N1 is related to N2 is related to N1. So this can be come down to very simple: N1 plus N2 minus N1 plus N1 plus N plus N2 square. Okay. So this is basically simplified to N2 N1 plus N2 square. Okay, so you can see this top term is basically what is the molar volume for phi 2, or this bottom is basically the total mode volume. So this actually can be written in several different ways. What this can be written as phi 2 square n. If we give it n2, this will be what we show above, or this will be phi 1, phi 2 divided by n1, right? So these are all equivalent to that. And this would be what is partial derivative of this phi 1 divided by n1. So if we know that, then we can plug this in back to what is long equation in terms of delta G partial derivative m1, or this we can also write as osmotic pressure, the unit volume divided by RT, and then we can just add in. So that long equation we saw in the last slide is going to be log phi 1 plus n1 phi 1, and this is going to be phi 1 phi 2 n1, and plus n2 phi 2 and minus phi 2 square n2 plus phi 2 minus phi 1 phi 2 and chi. If you had the partial derivative of n1 correctly for Gn, this you can take it slow and try a couple times on your scratch sheet and make sure you can get this right. This is a little bit long because there's 1, 2, 3, 4, 5, 6. There's 6 partial derivative coming down here because n1 multiplied by log phi 1 has 2 parts. If you have question here, you can let me know. Happy to walk with you. So what we now can basically simplify everything to phi 2, because phi 1 is equal to log 1 minus phi 2, and we know the phi 2 is also present in the second term, and plus chi phi 2 square. So that's pretty good. We now have a way to get what is the value of the phi 1, phi 2, and as well as other value. One approximation we need to do is, first, this term will be close to 0 if your n is very big. 1 divided by n will be very small compared to 1. Second is we need to take a Taylor expansion to what we know is this phi 2 is going to be minus phi 2 plus phi 2 square plus a minus 3 phi 2 cubical. So if we expand and do some approximation, this is what we will get. 1 minus phi 2 plus chi minus 1/2 and phi 2 square. Okay, so here is what we have talked about, and it doesn't seem we need to take this into 0 because it will be kept as here instead of we need to eliminate it, because this particular term is actually already cancelled out right here, so that's why we need to keep this 1 divided by n term. And if you saw here, it's already quite familiar with you what this is trying to do. This will be related to second variable coefficient of V2 term. This will be related to what is concentration. So let's take one more step as what will be defined as phi 2. This will be C V2 multiplied by N. And M is just a molecular weight, and C V2 because it's occupying multiple lattice, so it will be equals to number of n degree of polymerization multiplied by V1. Then we can further simplify this equation to exactly what we talked about in the class. Okay, this is how we relate to the Flory-Hagen theory to what we have shown here. The key part is where we need to understand what, sorry about that. We need to understand what is phi 1, take a partial derivative n1, and then we can understand this term. If you can get this, congratulations, it's a good job on your end to understand how these two are related. Okay?